In this example problem, we're going to design the following single and double corbels using the strut-and-tie method. We're given some information on the geometry of both the column and the ledge, and some information on the loading, and also our material properties. These corbels are common in precast columns, as the inverted T or L beams will come in and rest on the ledge from the corbel. So you can see a double T coming in, framing into an inverted T, and the inverted T resting on the ledge or the corbel of the column. And this photo is courtesy of Course Lab Structures Miami. Our first step is to determine the loads to apply to the member. These, in this case, were given in our problem statement. If they aren't given, then we would obtain them from the reactions of the members framing into the corbel. So in other words, we have our double T beam coming into our L beam or our inverted T, and then those beams coming into the ledge. So we can find the load coming in to our bearing based on the load coming in from the inverted T. Our next step is to estimate the member size, or the dimensions for the corbel. The corbel dimensions were given in this problem, but if they aren't given, a good starting point is here, where the corbel depth is about equal to the width of the column. Our corbel depth at the end is about half the width or half the depth of the corbel at the column face, and the corbel length about half the overall height of the corbel. So after this, we can determine our bearing pad size and our bearing pad location. Here we're going to start with a 6-inch by 12-inch bearing pad, and this is generally a good starting point, and then you can increase or decrease the size of it based on how, or if the capacity of the bearing checks. So here we go with our bearing check. Our phi VB is going to be equal to our phi factor here of 0.65 for bearing, times 0.85, times the area of our bearing, which in this case is 6 inches, times 12 inches, times the strength of concrete, which is given as 5 KSI. So this will give us a capacity here of 198.9 kips. And we can compare this to our V sub U, which is equal to 80 kips, and see that we're okay here. So now we can place the bearing. And generally we want the bearing to be close to centered on our ledge. It should be 1 to 2 inches from the face of the column, and so we can position it. So we'll position the bearing 1 inch from the face of the column. In this example, the bearing centered. We also need the distance from the center of the bearing to where the load would be applied, and typically that the load can be offset by 1 inch here. So the shear force can be shifted 1 inch away from the face of the column. So an additional 1 inch. So we'll need our AF or A sub F here, and this is the distance between the face of the column and the center of, or I guess the center of the force. So this will be 1 inch plus half of our bearing, so plus half of 6 inches, so plus 3 inches, and then plus this additional inch that the load shifted off. So our A sub F in the problem is going to be equal to 5 inches. Next, we need to divide our member into B and D regions. And we can find our D regions by extending, or our D region extends a distance of height of the column away from the geometric discontinuity, which in this case is the corbel. So H sub C up, H sub C down, this is our D region here. Our B regions are our surrounding regions, and we can use just our sectional design approach to design our B regions. So you can go back to our column example, and we can just develop our moment axial force interaction diagrams and plot our demand, and we want to make sure that our demand is inside the capacity moment axial load interaction diagrams. The D region is the region where we're going to use the strut-and-tie method to design, and that's what we're going to do in the rest of this example. Next, we need to create a strut-and-tie model for our D region and calculate all of our element forces. So we'll start with our strut-and-tie model for our single corbel, and we'll use red for tension. So I set up the nodes already. We kind of want the nodes on a grid, and we know that we want one node under our support here. So one node under the support. These nodes are dictated based on the location of the steel coming up from the column and the centroid of our compression block region in the column. So that's the location of those, and then B is just on a grid, so coming up from C and coming over from A. So looking at our tension ties, I guess our compression strut, so we'll have a diagonal strut coming over between A and D. We'll need to have a tension tie here to resolve the tension going to the right and left at node A. We'll need a diagonal strut here between B and D to resolve our tension that's going to the right at B from tie AB. And then we'll need a tie coming down between B and C to resolve the compression force that's going up into the left at B. So this is the simple strut-and-tie model that we'll use for the single corbel. For our double corbel, we'll have diagonal struts coming down between F and H, and between E and G. We'll need to resolve that horizontal force between G and H with a strut, and we'll need to resolve the horizontal force at E and F with a tie between them. So not having any loads above coming from the column, this is our simple strut-and-tie model for our double corbel. So we can find our truss geometry based on the location of our loads and the location of the reinforcement, and then here this will be based on the width of our compression block region. So, and then I guess we also need the vertical distance from the top of the ledge to the center of this tie. And that distance is dependent on the cover and the size of reinforcement used in our tie AB. So our cover here is going to be equal to 1.25 for number 5 bars and smaller. And we're going to start by assuming that we have a number 4 bar for our ledge reinforcement here. So half of that number 4 bar is going to be equal to, 0.5 times 0.5. So adding these up will give a distance of 1.5 inches. Our distance D is going to be equal to H, the overall height of the corbel, minus this distance that we just found, 1.5 inches. So D, the distance from the bottom of the corbel here to the center of our tie AB, is going to be equal to 14.5 inches. We'll also have an additional distance because if we resolve these two forces, we'll have a diagonal force coming in that's pointing down to the right. So the point where that force intersects our node A is going to actually be to the right of where that shear force is pointing down. So we can use our geometry and find our angle of that load by taking the tangent, with the tangent of that angle equal to our normal force divided by our shear. And then we can find the additional distance using this equation here. So we can add that additional distance to our AF then to find our distance D5, the distance from the face to the centroid of our node A, the horizontal distance. And so that'll be, will give us a distance of 5.3 inches. The distance from the side of the column to the center of BC is going to be dependent on the cover and half the diameter of the bar that we use in BC, and then also and then the diameter of our stirrups if we're going to have that bar hooked inside the stirrups. So in this case, we're going to assume number 4 bars are used for this hooked bar, and number 4 bars are used for our stirrups. So we'll have a distance D2 here equal to 2 inches. The position of our node D is going to be dependent on the strut width here of the strut coming in at D. So we'll use these equations again, but we need to find the effective concrete stress using our ACI equation from the strut-and-tie method section. Our node D is a CCT node, so we have compression coming in all directions except one, so one tension element. So CCT, one tension element, so that's the T. So we'll have a beta N factor of 0.8 and a beta C factor of 1.0. Or we're assuming a beta C factor of 1.0. We'll look at this factor again later in this example. Plugging in those values, we can get our effective concrete stress here of 3.4, and we can take that times the area to get our capacity here, where our phi for strut-and-tie method is 0.75. So right now we don't know the width. That's what we're trying to solve for. So we'll leave that as a variable W sub s. So we can then sum our moment about point C with our forces here. So the force coming in from our strut D, our force coming from our V sub U, and our force from N sub U. And we can plug those into this equation here. So force times lever arm between C and those different force components. And then we're going to solve for our only unknown, which will be W sub s. We can plug all of our known values into this summation expression and simplify it down into a quadratic and solve for our A, B, and C components, which I do here. And then we can use the quadratic formula to solve for W sub s, which we'll get here to be 4.63 inches. We can then use this 4.63 inches and solve for our D3 and our D4. So our D4 is just half of that strut width. So that's where we get that value. And our D3, we have the overall column width minus D2 minus D4, and we'll get that to equal 9.69 inches. So we now have all the dimensions we need for our model, and we can now calculate our element forces. We can next do the same thing that we did for the single corbel for the double corbel to find our position of our strut, our nodes G and H with the strut coming in from G and H here. So looking again, G and H are both CCC nodes because we have compression coming into the nodes in all directions, so no tension. And we can solve for the capacity of these nodes in terms of W sub s. And then we can do the same thing we did before, solving for our strut width by setting the capacity of this node equal to V sub U, since that's the only vertical force coming in. And solving for W sub s, we'll get W sub s equal to 1.79 inches. We can then use this to solve for our D7 and D9, which will be equal to 0.9 inches. And our D8 here, which is the distance between G and H, just by taking our overall column width minus D7 minus D9. So we'll get that to be 12.21. So now we have the dimensions that we need to also solve for our element forces in the double corbel. You can use whatever truss analysis method you'd like to calculate the forces in each of the elements. You can also use an available truss software if you'd like. It's better if you can try to set up a spreadsheet based on method of joints to calculate all the element forces though, because then if you need to change the geometry of your model, it'll automatically update the element forces, and then you can have those element forces referenced in your tie and strut calculations so everything can automatically update. So this will save you some headaches later, so you won't need to go back to the analysis software. So just a sample method of joints. We're going to look at our joint at point A. So at point A, we have a force coming in from a force AD, and that force is going to be an angle theta A off the horizontal. We have a force AB that's pointing to the left. That'll be a tension force. And then we have the two forces coming from our bearing. So we have V sub U pointed down and N sub U pointed right. So we can find our theta A, the angle of our inclined strut, based on just the geometry and our distances that we found on the previous slides. So we can use the angle and these forces then at some forces in the Y and some forces in the X and solve for the different element forces. So we'll start with the Y direction because we have one known force and one unknown force. So we'll use positive up. So we can have F sub AD times sine theta A minus V sub U pointed down, and this will be equal to 0. So solving for F sub AD, we'll have VU divided by sine theta A. So 80 kips divided by sine 62.3 degrees will give us about 90.3 kips. So this is the force that's in our diagonal strut there. So you can see that force there. So we can do the same thing in the X direction here and solve for F sub AB. And we'll get that to be around 56.9 kips. So that'll be our force here. Note that if you were to get a negative sign for any of these, then you know you assumed the wrong direction initially. So you'd have to just, instead of it being, whether a tie, it'd be a strut, or if you assumed a strut, then it'd be a tie. So we can do that for all of our forces in our single corbel and our double corbel, and we'll get these models with these element forces shown here. So we can use these then to design our ties and check the capacity of our struts and our nodes. Our next step is to design all of our tension ties. And we can do this using our design requirement for our ties from ACI 31819, where we have phi F sub nt is greater than or equal to F sub nu. If we only have pre-stress reinforcement, then our capacity of the tie is just going to be equal to the area of the tie times Fy. So we can substitute in and we'll get this equation here. So we can find our reinforcement then is going to be equal to F sub nu divided by phi sub y. So plugging in our values, we'll have our F sub nu for our tie AB, which is 56.9 kips, divided by phi 0.75 times 60 ksi, which will give us an area equal to 1.26 square inches. So this is our required area, and we need to figure out what combination of what bar size and what number of bars we can get to provide that area of steel. So we can try number 4 bars, we can try number 5 bars and number 6 bars. So this is the area of each one of those bars and the number of bars required to provide that 1.26. So we would need 7 number 4 bars, 5 number 5 bars, or 3 number 6 bars to get that area. So we need to see if we can fit these bars or this number of bar into the width of our column. So we're going to first try our 7 number 4 bars and use the width check from our section 2521 in ACI 318. So doing that check, we can plug in all of our known values. So our known cover distance and diameter of the stirrup, diameter of our bend, which is given, and the number of bars and number of spaces. So we'll get our check to be equal to 14.5, which is greater than the column width 14 inches. So we can't fit those 7 bars into our column width. So in this case, we can't fit the bars, so we can try increasing our bar size and seeing if we can fit 5 number 5 bars into the column width. If we try our 5 number 5 bars into the same equation, we can see that our design check will give us 12 inches, which is less than our column width, 14 inches. So it's okay in this case. So we can move forward with our 5 number 5 bars and just checking to make sure we're providing the area required. We can see that the area provided is greater than the area required. So this tie is designed okay, tie AB. Next, we can look at our tie BC. Our force in tie BC was 85.2 kips divided by phi Fy gives us an area required equal to 1.89 square inches. There are several different bar configurations again we can try. We want to try to have one bar that's the same for AB and BC, so we'll have one bar kind of hooked down. So we're going to start with trying a number 5 bar, and we'll try 7 number 5 bars. So looking at our check with 7 number 5 bars, we can see that we don't have a sufficient width in the column to fit those 5 number 5 bars. So we can try moving up to our number 6 bars next. Here's the check for our 5 number 6 bars, and we can see that we can fit those 5 number 6 bars into the column width, so we're okay. So we can check that the actual capacity then one last time. So we have 5 number 6 bars, the area provided versus the area required. So that tie is designed. And we're going to use one bent bar from A the whole way to C. So we're going to assume then that for AB and BC, we're going to use 5 number 6 bars. The last tie that we have is this tie CD, and we'll have a force of 15 kips divided by phi Fy 0.75 times 60, and we'll get an ATS required equal to 0.33 square inches. So this is less than what we'll need for our crack control reinforcement. So we're just going to satisfy the tie requirement here with our crack control reinforcement. Note that we assumed initially that we had number 4 bars for our tie A, B, and BC. Because we're changing to number 6 bars, it's going to change our cover and the distance from the top of the ledge to the center of our ties. So we'll need to adjust our geometry and go back and recalculate all the forces in our model. So this is why it's helpful to set up a spreadsheet. So if we provide these 5 number 6 bars, when we modify the geometry of the strut-and-tie model and recalculate forces, we'll get the forces that are shown here. You can see these forces are slightly different, slightly higher, but they're still, all of our ties that we designed will still check with these additional forces. Next, we can design our tension ties for the doubled corbel. So in our double corbel, the only tie that we'll have is EF. So we can find the area required for EF and look at the bar size and number of bars required. For the double corbel, we can use 6 number 4 bars, and we can fit those 6 number 4 bars into the width. So that's what we'll provide. So, and because the number 4 bar in the double corbel is the same as what we assumed, our strut-and-tie model doesn't change, so our element forces will all be the same. Our next step is to check the stresses in the nodal zones with defined shapes and sizes. So we only need to check the nodes where we have a defined geometry. In other words, non-smeared nodes. For our single and double corbel, I'm highlighting the nodes that we need to check. A, E, and F have defined geometries because of the bearings, and these are all going to be CCT nodes. Node B is a curved bar node because we have one bar that makes up our tie AB and BC. So we'll have a curved bar node that we'll need to check at node B. So for our single corbel, we need to check our node A, and this is a CCT node with a geometry that looks like this: back face, bearing face, and the strut width. So we'll look at how to calculate the capacity of each one of these faces. We need to make sure that our struts and our nodes have sufficient capacity in ACI 318, and our phi factor for strut-and-tie in ACI is going to be 0.75. I'm showing you all of the different ACI 318 strut and node checks on this slide. So here we can find the capacity of our strut, the effective concrete strength of the strut. We have our different beta factors for our strut in this table here. So based on whether we have a boundary strut or an interior strut, or if we have a strut where there's tension in that element. For our nodes, we can find the capacity of the node using this equation with our effective strength for our node, and the node at effective concrete strength, our beta N factor, depends on the type of node we have. A CCC node where all compression elements are intersecting at the node, a CCT where we have one tie element, or CTT where we have two or more ties and one compression element, or at least one compression element. So the beta C factor is a confinement factor, and the confinement factor takes into account if our bearing area is smaller than the concrete area beneath it. So assuming that we can have a load spread and that the surrounding concrete will help to confine the concrete under the bearing. So we can increase the capacity if this is the case by this beta sub C factor. We can now calculate the capacity, or our confinement factor, and then we can calculate the capacity of our node and strut at node A. So we can start by finding our bearing area, and our bearing area, we have a 6-inch by 12-inch bearing. So we'll get an area here of 72 square inches. Our area 2 is our extended bearing area. So our load can spread until we intersect the edge here. So we can find our extended bearing area by taking 6 inches plus 2 inches, which is it can spread 1 inch and 1 inch on each side, times 12 inches plus 2 inches. And again, because we're spreading equally on all sides, we can also spread an inch on each side on the top and bottom. So the distance of spread should be equal in both directions. So here we have 6 plus 2 times 12 plus 2 is going to be equal to 112 square inches. So our confinement factor then is equal to the square root of 112 squared divided by 72 inches squared. Sorry, 112 inches squared divided by 72 inches squared, which will give us a beta sub C equal to 1.25. This is less than or equal to 2, so we can use a confinement factor equal to 1.25 in this bearing. So for our struts and nodes, we can find our effective concrete strength. We have 0.85 times beta sub C, 1.25. Our beta sub S, we have an interior strut, so we'll have a 0.75 factor here, and then 5 KSI concrete. So we'll get an effective concrete strength equal to 3.98 KSI. And doing the same thing for our nodes, 0.85 times 1.25. We have a CCT node, so looking back on the last slide, we can use a beta sub N of 0.8 times 5 KSI will give us F sub CE equal to 4.25 KSI. So those are our effective concrete strengths. Next, we need to find the areas and the forces on, and the areas and the capacities of our different faces. And we can start with our back face height. So our back face height is going to be 2 times the cover plus 0.5 d sub b. So in this case, we'll have 2 times our cover, which is 1.5 inches, plus 0.5 times 0.75. So this will give us a value here of 3.75 inches. Our area then is going to be that height, 3.75, times the width of the back face, which is 14 inches, which will give us an area of 52.5 square inches. We can use that area of the back face to find our capacity and then check that capacity versus our demand. So our capacity is going to be 4.25 KSI times our area, 52.5, which will give us 223.1 kips. And we can take that times 0.75, which will give us a capacity here, a factored capacity of 167.3 kips. And we can compare this to our F sub U N, so the back face, which will be equal to our tie force, 58.8 kips. So our first check's okay. Next, we can look at our bearing area. And our bearing area, the area is just going to be 6 times 12 inches, 72 square inches, times the effective concrete strength, 4.25 KSI, will give us a capacity of 306 kips. And we can take that times 0.75, our fee factor for strut-and-tie, to give us a factored capacity of 229.5 kips. Compare this to the 80 kip shear force coming down, and we can see we have sufficient capacity for the bearing face. Next, we have our strut to node interface. And we need to first calculate the strut to node interface length. The equation that I'm using is given in ACI. So our WS is going to be equal to the length of the bearing, 6 inches, times sine times our theta sub S, 61.3 degrees. And remember that these new dimensions and angles that I'm using are based on the updated strut-and-tie model geometry with our number 6 bars. So you can calculate those on your own if you want. All right, so we have plus the height of our back face, 3.75 inches, times cosine 61.3 degrees will give us a strut width of 7.06 inches. We can take that times the thickness of our column, 14 inches, to get the area of our strut to node interface, 98.9 square inches. And then we can take that times our effective concrete strength, 4.25 KSI, times 98.9 inches squared will give us a force here of 420.3 kips. We can take that times 0.75 to get our factored capacity of 315.2. And we can check that against our demand, which we can see is 91.2 kips. and we can see we're okay here. The last thing that we'll need to do here is the first check here is the node check, but we also need to check the strut side of it. So using our effective concrete strength for the strut. So we'll take that effective concrete strength for the strut times the area, which will be the same, 98.9, to get the capacity here of 394 kips. Take that times 0.75, our reduction factor, our phi factor is the same, and we can see that the capacity of the strut is sufficient as well. So the capacity of our node A in the single corbel is okay. Our next check for our single corbel is going to be the curved bar node check. Because we have a continuous bar going from A to C, so we have 5 number 6 bars curving here, we're going to get a curved bar node here at node B. And essentially what this curved bar node check is in ACI 318 is we want to make sure that the concrete doesn't crush coming in from this strut in the bend radius of the curve. So we need to provide a sufficient bend radius for that bar. So for this, we need to find the area of our steel. So we have 5 number 6 bars, which will give us an area of 2.2 square inches. And then we can plug that into our curved bar node check. So 2 times 2.2 times 60 KSI, the yield strength for that steel. Our B sub S is our column width, 14 inches, and our concrete strength is 5 KSI. So we'll get our bend radius needs to be greater than or equal to 3.77 inches. And that'll provide sufficient capacity so we don't crush our concrete in that bend radius. So this was all for the single corbel, and we can go back through and check our nodes in the double corbel as well. Our nodes E and F are very similar to node A, and we can see that if we went through and did the checks, all of our stresses would check for those elements as well. Our next step is to proportion the crack controlled reinforcement. We're going to provide crack control reinforcement only in one direction, horizontally. And in ACI 318, we can, or if we provide reinforcement in one direction, then we need to meet this limit shown here, where the angle alpha is dependent on, is based on the strut angle and the angle of the reinforcement. So we have 2 different angles, our alpha 1 AD and our alpha 1 BD, because we have 2 struts that will be crossing this reinforcement. So we can calculate the angle for both of those using just geometry. So our alpha 1 AD is going to be equal to 61.3 degrees, and our alpha 1 BD is going to be equal to 56.8 degrees. And we can then use these angles in this equation to calculate for our required steel and spacing. We'll assume that we have 2 legs of a number 4 bar for our crack control reinforcement. So that'll give us an area of 0.4 square inches. So we can take that area, or we can then use that area to find the minimum or the maximum spacing for the bars crossing strut AD and BD just by rearranging the equation from the previous slide. So first looking at strut AD, we'll have 0.4 square inches times sine of 61.3 degrees squared divided by 0.0025 times 14 inches. So our spacing across AD needs to be less than 8.6 inches. And we'll have a different angle for strut BD, so we need to calculate that value as well. So 0.4 inches squared times sine of 56.8 degrees squared divided by 0.0025 times 14 inches, which will give us a maximum spacing here of 8.0 inches. So for our single corbel, we have strut AD and strut BD and the same crack control reinforcement crossing both. So we can provide 3 number 4 bars crossing that strut. And if we do that, we'll get a spacing of about 5 inches, which is less than that 8 inches. So that'll satisfy the minimum crack control requirements for our single corbel. For our double corbel, we can see that the 2 inclined struts are going to have about the same angle as our strut AD from our single corbel. So if we provide the same reinforcement of about 3 number 4 bars, and we'll get the number 4 bars spaced at 5 inches, and that'll meet our requirement. ACI 318 has a few additional requirements for corbels that we'll go through in our next step. The first requirement is our tension reinforcement limit requirement, and this requires that our primary tension reinforcement in the corbel be greater than the equation shown here. So calculating that equation for the column, it'll be the same for our single and double corbel. We'll see that our primary tension reinforcement needs to be greater than or equal to 0.67 square inches. So our tie AB and our tie EF provides the primary tension reinforcement in the single and double corbel respectively. And you can see that both ties are greater than, or the area of reinforcement in both ties is greater than that tension reinforcement limit. So we meet the first check here. Our second check is a shear limit check, and the ultimate shear V sub U divided by phi needs to be less than or equal to the minimum of these 3 equations. So plugging in our known values for these 3 equations, we can see the minimum of those would be 177.1 kips. And we can see that the demand, when we divide by that 0.75, is 106.7 kips, which is less than or equal to the minimum here, or that limit, 177.6 or 177.1 kips. So we meet the shear limit requirement. We also need to make sure that the bars in this tie are properly anchored so that we can develop tension right when we leave the node. And we don't have enough room typically to use a hook or a head or something. So ACI provides a couple different options. One is to weld a bar here and add a framing bar. So they give some details on the weld requirements. The other option is to provide a steel angle. So we can provide a steel angle here as well, and it's also helpful to have these framing bars to help frame out the ledge. So anyway, these are the 2 main options for making sure that we can anchor this tie here, so the tie bar and the ledge. And note that if we are welding, we need to make sure that we use reinforcement that can be welded. So it needs to be weldable reinforcement. The last additional check is a shear friction requirement check, and we need to make sure that we don't shear off the ledge. So that's what this check does. We're assuming that the corbels cast at the same time as the column, so our friction coefficient, or mu, is going to be equal to 1.4, and that's given in ACI 318. And then we can determine the amount of reinforcement crossing the friction plane. So in both cases, we'll have a friction plane right here at the ledge. So we're going to assume that we have all 5 number 6 bars. So we'll have 5 times 0.44 square inches. And we're going to also assume that we have 2 number 4 bars crossing. So we'll have plus 2 times 0.2 square inches. So we'll get a total area of reinforcement crossing our friction plane equal to 2.6 square inches. We can use then our shear friction capacity equation from ACI. So we'll have 1.4 for monolithically cast concrete, 2.6 square inches, and then Fy is going to be 60 KSI. So we'll get a shear here equal to 218.4 kips, and we can take that times our phi factor, which will be 0.75 for shear. Which will be 163.8 kips, and we can see that this is greater than our V sub u, which is equal to 80 kips. So we're okay here. We can do the same thing for our double corbel, and again, we have 6 number 4 bars, and we'll say we have 2 additional number 4 bars. So we have a total area given there, and we can take that area times our friction coefficient times the yield strength of the steel to get our capacity 134.4. Take that times 0.75 to get our factored capacity of 100.8 kips, and compare that to our 80 kips for a single ledge. So we're okay here for the double corbel as well. So with that, that's our last check for ACI 318. So that concludes this example. We can see that we found our dimensions for our corbel, and we found the primary tension steel and the additional steel that we need for our struts.